Oh dear. Okay, this is component 3 Mock 2, question 4. And we're up to question 4. So, question 4 has got a lovely action potential graph here, so that's good. That should immediately key you into the fact that this is about the nervous system. And question 4 starts, the symptoms of multiple sclerosis, which, no, you've not heard of them, so therefore the question's going to tell you the information you need so you can put the stuff you know down. Include delayed reaction times and visual impairment. Alcohol can also delay reaction times. The diagram shows the changes in potential difference across the membrane of a neuron during the passage of an action potential. So I'm just scanning through to see, do I need to actually write on that graph at any point, or can I can go for it. So there's a calculation on the next page. Looking forward to that. So, so now I can start annotating, and so I've got action. Remember that sodium move in, this is repolarization, and that's potassium out. We've got hyper there, and we've got, doesn't matter where you put it, resting. And what do I know about that? Sodium potassium pumps, and that ratio 3:2. And then we've got the time taken for the action potential to happen. So, describe how resting potential is maintained. So I don't need to write down now everything I know about the nervous system. I don't know how many times I've read an account of resting potential, and it's gone right through resting potential, action potential, hyperpolarization, repolarization, the whole kit and caboodle, and it's taken up, a page of extra paper. And really all the marks sort of come at the beginning, or if there's action potential in the middle. In the meantime, you've wasted your time writing about membranes for 20 minutes. Read the question. Resting potential. We're only going to talk about resting potential. So we've got sodium potassium pumps. Move 3 sodium ions out of the axon and 2 potassium ions into the axon. And that's your sort of basic information. Sometimes that's worth 2 marks, so always worth writing down the numbers as well. The membrane is more permeable to potassium ions. So they leak out. The inside of the axon is more negative as there are more positive ions outside and more organic anions inside the axon. And you could of course refer to proteins having a negative charge. So that's what is helping to keep that. I would always be very tempted to say what number it is. However, you've got a graph with the number on, so you're not going to get a mark for that because it doesn't say with reference to the graph. Okay. A strong stimulus at point A depolarised the axon membrane and resulted in a change in membrane potential seen at point B, which is the action potential. Explain why and how the action potential was generated. So, action potential, Y is the threshold potential was reached. So we need to refer back to the question, why. So the threshold potential of, and I'm going to give a number to that, just in case, that's worth a mark, was reached. So sodium ion channels open and sodium ions rapidly diffuse into the axon. Now do be careful here, because one of the really common errors on exam papers when you're writing about depolarisation, repolarisation, resting, is to talk about ions diffusing into membranes, and they don't. They diffuse across membranes, sure, but they're diffusing into the axon. So, you know, don't have them diffusing into the membrane. They won't, will they, because of that hydrophobic layer in the middle. So that'd be impossible. And part 2, suggest why the hyperpolarisation seen at point C makes it difficult to transmit another action potential. So if it's more, so if you think, right, okay, my threshold's there, you have to get to that potential difference, or here you've got to get more potential difference. So that's what they're asking you about here. So the axon is more negative than at resting. That explains what you're describing, what hyperpolarisation is, and it definitely in questions, if you sort of do a description, that will lead you then into the marking points, but often the description is worth marks, so in this case that's certainly the case. So the axon's more negative than at resting potential, so threshold is harder to reach and needs a stronger stimulus. Okay. And then we've got a lovely calculation here. I can tell there's a calculation because there's a blank box. So, need to read the information. Nerve impulses travel along different types of neurons at different speeds shown in the table. So 0.08 meters per millisecond in sensory, and slightly slower, no, faster, at 0.12 meters per millisecond in motor neurons. So here we've got a receptor, synapse, sensory neuron, it tells you how long it is, so that's probably what they're going to ask you to calculate, with its cell body, another synapse, motor neuron cell body, motor neuron, and a muscle. So, it tells you that the receptor is 0.9 meters from the spinal cord, and that's handy because it shows you that there. There's a delay at each synapse or neuromuscular junction of 2 milliseconds. So I'm going to slow it down there, 2 milliseconds, 2 milliseconds. Calculate how long, and here, 2 milliseconds. Calculate how long it would take for an impulse to be transmitted along a sensory neuron, so I'm going to start there, from this receptor, and back along the same length, so that's also 0.9 meters. Motor neuron to a muscle. Show you're working. Excellent. So let's do the time. We will need to work out how long it takes for it to go along the sensory neuron at 0.08 meters per second, millisecond, and then how long it takes to travel that way with the motor neuron, and then we'll need to add on our 2 millisecond delay at these two synapses. So we do the sensory one first. So for the sensory, the time would be 0.9, which is the distance, over 0.08. Trusty calculator, I think it'll be good enough for this one. 0.08, that's 11.25, and that'll be in milliseconds. And then the motor time, we've got the same distance, 0.9, but now our transmission speed is 0.12. So 0.9 divided by 0.12, 7.5. And then we've got 2 synapses. 2 times 2 milliseconds, which is 4, and then we just need to add those numbers up. So I've got 7.5 plus 11.25 plus 4, 22.75. And just read that question again, because I will need to know. I'm dithering about whether to include this one. From this receptor along a sensory neuron. So I've got 3 synapses, haven't I? From the receptor you've got a synapse, then sensory neuron. So that'll be 3 2s, 6. I'm going to go for that. Plus 2. That'll be 24.75. That kind of assumes there's no distance. The receptor's detecting it. There's nothing. That's not a nerve. You've got a synapse then. 0.9, 0.2, 2 milliseconds. 24.75 milliseconds. Now I always, in an exam, I would do the calculation twice and also think back, do I need to include, what do I need to include? Because, no, if you get a calculation right, it's 3 easy marks, isn't it? So, multiple sclerosis is caused by the immune system destroying the myelin sheath. So, I'm already thinking, no saltatory conduction, can lead to delayed reaction time, suggest why this condition leads to a slowing down of the transmission of a nerve impulse. So I'm just going to do a little plan, because I'm going to have to put it in a nice logical order. So I want to say that there's no myelin, no saltatory. So why will it be slower then? So I need to perhaps talk about local circuits. I need to say perhaps all the neuron works like that. Do I need to? I don't know. I could talk about I could talk about the nodes. No nodes to lengthen the circuit. Put that up there, with there. Anything else I could talk about? Might use the word more so that it explains why it's slowing down. So now I need to decide where to start, so a little sort of plan in my head, and I'm going to start with without myelin. So without myelin, there is no saltatory conduction, and I'm going to just explain what that means. Where ion, I'm going to call it exchange. I'm swapping one for others. An ion exchange takes place only at the nodes of Ranvier. What does this mean? This means that local circuits so I've got saltatory, I've got no nodes, local circuits are formed all along the membrane. So more membrane has to depolarize, which takes longer. Normally circuits are between nodes of Ranvier and the conduction is faster. So I've told both halves of that story there. I've said, you know, right, okay, we know saltatory conduction. I've said what's saltatory conduction is, what the multiple sclerosis effect will be, why it causes a slowing down, and then back to the beginning again to say, okay, if we've got saltatory conduction, that'll be faster. And I'm pretty sure then that I've told them everything that I know. So, alcohol has an inhibitory effect, and this time we're talking about synaptic transmission. So, suggest two ways in which they could decrease the speed of transmission. So here, we're talking about that bit. So what could stop that happening? So I'm thinking normal transmission is you've got calcium in, vesicles fuse, release, binding to receptors, depolarization. That's normal. So if you block a receptor, if you stop the calcium ions going in, so these are all our inhibitory ways, or if we make this more negative, remember GABA, all of those will stop it. And so it suggests, so that means there's more than one right answer, but they've got to be biological sense. So alcohol could block calcium ion channels, so neurotransmitter not released. It could block receptors, so neurotransmitters can't bind, or it could cause hyperpolarization, making threshold harder to reach. And any of those I think would do. And my final warning to you is that the effects of alcohol, they have more effect, the same amount of alcohol has more effect on a teenager than it does on an adult, which is why it's okay for adults to drink, but not for you.